Okay, there's one last thing I wanted to do today, and that is to talk about a shorthand that we use for talking about variables. And this is just something we use in this class to do truth tables and write down what we know. So there exists X, and for all X are propositions, and they are talking about how often something like P of X is true. So I'm going to use this shorthand to help me figure out truth values. So sometimes I have to look at P of X without a quantifier on the front of it, and I need to talk about how often it's true or false. So if I make the statement, for all X P of X, this is a proposition, right? It can be true or false. And I can make another proposition that's also true or false. And I can AND them together because they're propositions, and I can do whatever I want with propositions and operators. We've been doing that for a while. So I can actually make a truth table for this just like I normally would. Each one of those is propositions. I can use them as propositions. I can AND them together, and I get the same normal stuff. But if I start trying to understand like what this actually means, I need to be able to write down some shorthand that helps me understand it. Okay? So what I'm going to do is I'm going to make a column for P of X, and I'm going to make a column for Q of X, and then I'm going to talk about how frequently P of X is true and how frequently Q of X is true. So I know that in row 1, remember that each row is like the state of the universe. In row 1, I have that for all X, P of X is false. So that means that there's at least one counterexample. That means there's a P of X that's false, right? So I have at least one false. So the reason why we have the shorthand is because they actually correspond to the zeros and ones for our quantifiers. So if I have a for all and it is false, then I have at least one false for the function that's on the inside. No matter how complex it is, that for all means that whatever that thing on the inside is, there's at least one false for it if for all X P of X is false. And since this is a 0, it'll be exactly the same. Now, if I'm in the third row, which says for all X P of X is true, then I actually know that P of X is always true. And I have the same thing for there. So over here, I have for Q of X, that for all X, Q of X is false, and I can fill it out exactly the same way. So if I have a for all, if that is false, I get at least one false. If it's true, I have all trues. So what we might want to use this for is to look at something like for all X, P of X, and Q of X. So first of all, we need to know what this actually means. So if I'm seeing if these two things are equal, I want to actually show that these are logically equivalent. Then I need to know how often P of X and Q of X is. So what's the difference between what's on the left and what's on the right? What's the difference between for all X P of X and for all X Q of X and for all X P of X and Q of X? So let's translate into some English sentences, and let's make P of X, X drives a Porsche, and Q of X means that X is a quitter. Okay? So if I say everyone drives a Porsche, if that's true, and everyone's a quitter, is it true that everyone is a person who drives a Porsche and is a quitter? Yes, it does. But what I've actually done is over here, I only have one variable. So when I'm talking about P of x right here, I have to be talking about the same person here. So P of x and Q of x with the same quantifier actually means that these x's have to be the same all the time. And that means I'm talking about this Porsche driving person as a quitter. Okay? Over here, these Porsche people can be different than these quitter people, right? Because these are different quantifiers. So even though it's the same letter, these x's and those x's don't have anything to do with each other, but these do. Yes. Yes, yes, you can. You can, but you can't over here. So over here I have to, right? So these could be different domains. So the question was, can I use x's from different universes? Yes, I can. And I can or and add these together any way I want if they're separate. If they're not, then I have to somehow make the universe the same, right? So I'd have to restrict the universe on both sides to even talk about what this statement means. Okay? So what I do is I use this shorthand, assuming that my domain is the same on the left and the right. I'm going to use the shorthand to figure out how often this P of x and Q of x is true. So if I and, so right here, I'm actually going to and the P of x with the Q of x. So there's a way to do it, but it's not straightforward, right? Because these aren't actually propositions. So, but remember that ands preserve falses, okay? So if I and two of these frequency things together, I'm going to save the most falses that I can. So if I and at least one false with at least one false, how many falses do I have? At least one, right? So for this P of x and Q of x, I'm going to have an at least one false. And the same thing's going to happen in every row except for what? The last one. I'm going to have P of x is always true and Q of x is always true. That means no matter what I plug in, I get a true. And a true and with a true always gives me true. So I'm going to get an all true if I and those together. So we're going to talk about those some more next time, but just remember now we're going to look at this quantifier and say, oh, that's at least one false. So for the for all quantifier that gives me zeros, and for all true it gives me a 1. And we'll see you next time.